We're going to get started with the session. And so, just to give you a quick introduction, um, welcome to the Hands-on Simulate series. So, this series is essentially aimed at providing users a hands-on experience with SimCenter Star CCM Plus. So, in this series, we'll be solving some of the toughest industry problems using the tool's advanced capabilities. So, today is an introductory session where we will cover an overview of the tool and also have a live demo of setting up a flow problem, that is a Francis 99 turbine. So this session will be followed up by industry-specific problems. Note that though these problems may be pertinent to a specific industry, each session is aimed at introducing features that are cross-domain. Such as when dealing with battery simulations, you're working with hundreds of parts. In tow tank simulations, you're simulating models to scale. And with vehicle thermal management, you usually work with large complex conjugate heat transfer cases. We will show how Star CCM Plus has an integrated, streamlined workflow to resolve all these issues. So the agenda for today is essentially we'll go through an introduction of Star CCM Plus. We'll go through the history and philosophy, an overview of the capabilities, and then finally, we're going to dive into a live demo, starting all the way from geometry to post-processing, as well as design exploration throughout this workshop. Now, just a reminder that the session is recorded and will be provided to you towards the end of today. And if you have any questions, please don't hesitate to drop it in the dialog box, the GoToWebinar. And so some of these questions we'll try to answer them today. If not, I will get back to you via email. So before we begin the session, let's go through some of the challenges that are faced by CFD engineers. So nowadays, it's very common for CFD engineers to use multiple software tools to get results from a single simulation. There will be a given tool for CAD cleanup, another one for meshing, solving, and another tool for post-processing. Such tasks result in disconnected processes. Any changes in the CAD, for example, will not relate to changes in the mesh and boundary conditions and so on. So this often leads to organizations developing their own scripts, which are generally valid for a given release. Now, scripting is not limited to just processes, but also multi-physics simulations. So commonly in simulations for, let's say fluid structure interactions, we have separate tools for CFD and structural simulation that need to be connected. And this is often done via, file transfer. So this leads to inefficiencies and very slow solve times. Now, CFD engineers are also limited to analyzing a given problem. Now, in consulting projects, I would be generally asked whether a given design would meet the requirements or not. And if they didn't meet, I was only limited to giving suggestions based on engineering solutions or intuition. Now, optimizing a design for a given problem is usually not discussed, as there is a general consensus that these are too difficult to perform. Moreover, they need too much computational power, and the more computational power means increased costs and licensing, as well as hardware costs. Essentially, if we were to sum up these challenges, the issues we face is that CFD engineers spend more time building the CFD models than exploring the design space. Now, Star CCM is designed to counter this. The philosophy with which the tool is designed is to discover better designs faster. So before I begin, let me give you a quick elevator pitch to what SimCenter Star CCM Plus is and what the series is all about. Now, SimCenter Star CCM Plus is a CFD-focused multi-physics engineering solution that uniquely integrates comprehensive multi-physics with intelligent design exploration in a single CAD to solution environment. So it's built for the most simple to the most advanced CFD needs. Now, from this pitch, the first thing I want to highlight is that it is a single integrated environment. All the stages of the simulation, pre, solving, and post are done in this one single environment. Now, within the single environment, you have an automated workflow. What this means is that once you've built your first simulation file, you can automatically update your design changes without any effort. Now, the first 2 points are focused on how SimCenter Star CCM Plus is built to reduce engineering time to set up the simulation. Now, this third capability of SimCenter Star CCM Plus is really focused on model realism by bringing a very comprehensive range of physics models. Now, single scenario engineering simulations are about to become a thing of the past. As I mentioned just earlier on, CFD engineers have now expanded their capabilities to more than just troubleshooting a given design problem, but to finding the optimum design solution in the design space. And with SimCenter Star CCM Plus, design exploration is a fully integrated component of the platform. So we've talked about productivity to save engineering time, but what about efficiency and productivity of the tool itself? Things like ensuring simulation runtimes and licensing costs to turn them around quickly. Now, this brings me to the next 2 points. Now, SimCenter Star CCM Plus is parallelized from CAD to solution and scales to hundreds of thousands of cores with a flexible licensing scheme, giving you the best bang to your buck. Integration with Teamcenter for simulation and data management is within the given tool. Finally, becoming a SimCenter Star user means more than purchasing a world-class software. Our technological solutions are backed by a global team of engineer analysis specialists dedicated to help tackle your challenges. Now, when it comes to our customer support, we go above and beyond, which is always a winning criteria for majority of our customers. That we've heard customers tell us that in terms of our customer support, we rank 14 out of 10. Now, the next part of the presentation, I'd like to go into understanding why SimCenter Star CCM Plus is designed for design exploration. And there is a cliche saying as to know the past, you need to know the future. So before we talk about the current capabilities of the tool, to know what the future looks like, it's important to understand where the tool has come from. So let me just show you the history of Star CCM Plus. Now, SimCenter Star CCM Plus was founded 15 years ago, and in terms of industrial CFD, 15 years is not a very long time. Now, the first version was released in 2006 with its single integrated environment and client-server approach. Now, this was the real shift in how CFD was done. From the start, there has been a rapid growth in capabilities, and one of the first things that was introduced was the mesh pipeline. It also became the first industrial CFD code to leverage polyhedral meshing. Now, with the price of computational hardware becoming cheaper, licensing costs were starting to become the limiting factor in terms of hardware adoption. And this is something that we see and face currently as well. So in 2010, Star CCM Plus broke that paradigm by introducing the Power Session license. It allowed parallel simulation on an unlimited number of cores for a single fixed cost. Then in 2012, it was the first industrial code to introduce overset meshes, enabling users to more easily model moving mesh scenarios. Then in 2015, the finite element solver was integrated for fluid structure interaction. In 2017, Star introduced the Design Manager, which is a fully integrated approach enabling design exploration and optimization from within SimCenter Star CCM Plus. Now, earlier this year, Star CCM Plus introduced the industry's first inbuilt adaptive mesh refinement for free surfaces and overset mesh. Bringing us right up to today, it continues to grow the automation capabilities, the exploration tools, the comprehensive multiphysics, and also the industry-leading data analysis, including collaborative virtual reality. There's a lot more that has been done in this time frame. This should give you a taste of how far this product has come in such a short space of time. Now, the question arises, how did Star CCM Plus go far so fast? Now, one of the key reasons is that the SimCenter Star CCM Plus has releases 3 times every year. So with this very aggressive release schedule, they were able to deliver on an average of 300 new features each year. And this has allowed SimCenter Star CCM Plus to grow into the tool it is today. One of the things that the development team utilizes to help decide what features they bring into the code is IdeaStorm. It's a crowdsourcing system that allows you as customers to submit your ideas for code improvements. Developers use that to interact with users and understand where they need the code to go. Just in 2019, out of the 350 new features, over 100 of those were born in IdeaStorm, giving you the ability to shape the tool. So what is it about SimCenter CCM Plus that makes it different from all the other CFD tools out there? So I want to tell you the story around 4 important pillars that define SimCenter CCM Plus. First, we're going to talk about the high fidelity digital twin. How can you handle more complex geometry and more complex physics within SimCenter CCM Plus so that you can have the confidence in your design decisions? The second pillar is all about going from a single design point to hundreds of design points so that you can drive innovation and stay competitive. Now, of course, providing a high fidelity digital twin and running hundreds of designs, these are great things in theory. But unless you can make those decisions in a reasonable amount of time, that value is lost. Our third pillar is therefore about making sure that SimCenter CCM Plus helps you make decisions in hours and not weeks. This is achieved through fast simulation throughput and the ability to quickly extract insight. And finally, SimCenter CCM Plus is part of the Accelerator portfolio. By linking these other tools within the Siemens Digital Industry software, we help accelerate and build on your digital future. Now, let's jump right into a complete overview of the tool so that we have an understanding of its full capabilities. So in terms of the overview, we are going to review the workflow of CCM Plus from geometry generation, then define the physics. We'll talk about mesh generation, simulation, the multi-physics capabilities. We'll look at the post-processing capabilities by analyzing the results. And then through this pipeline workflow, explore the design space for the most optimum design. So we're going to dig deep into each of these steps, give you an overview of CCM Plus, and then actually build the model from scratch, from geometry transfer all the way to design exploration for today's demo. So the first thing in terms of geometry is that CCM Plus has a built-in parametric 3D CAD tool within the software. But as I mentioned earlier on, the key feature for SimCenter CCM Plus is not just looking at a given design, but it is exploring the design space. And the key to design exploration is parameterizing the model. Now, this can be done within SimCenter built-in 3D CAD tool, but it also has bidirectional CAD connectivity with tools like Inventor, Creo, CATIA, and NX, where you can import those parameters of your CAD directly into CCM Plus and have a bidirectional associativity. What that means is any CAD changes in Star will be updated within the CAD tool as well. I will be showing an example of this in the live demo as well. And here is a video showing synchronous modeling capabilities in NX, where you can basically import any CAD and perform operations on its surfaces. We will be showing similar features for today's demo. Now, once you've parameterized and imported your geometry in the CAD tool and conducted your simplification operations, the next step would be the meshing. Now, one of the key highlights of CCM Plus is its meshing capabilities. So one of the key highlights of CCM Plus is its flexible and robust meshing. Now, this is very much required to cope up with the automatic design changes done in design space exploration. So when the CAD is changed, the mesh needs to adopt automatically. Now, this is realized in SimCenter CCM through the fully automated meshing process. Now, there are 3 core meshing types in Star: the tetrahedral, hexahedral, and polyhedral. Now, the polyhedral is good for swirling or highly anisotropic flows and heat transfer between the fluid and solid region. Just to mention this again, the entire meshing pipeline within CCM Plus is parallelized, so you can take advantage of all your cores in the meshing process, reducing the time for pre-processing a given CFD simulation. Now, the next thing I wanted to show is the various mesh motion capabilities within Star. So you have the overset or chimera mesh morphing, rigid body motion, as well as sliding or rotating mesh, as well as rotating frame of references for turbomachinery applications. All these capabilities provide you the ability to run complex simulation with less computational resources. But as mentioned earlier, through the history of Star CCM Plus, just recently they introduced the first industry's first model-driven adaptive mesh refinement for free surfaces and overset mesh. So the adaptive mesh refinement refines the computational mesh dynamically in only areas where it's needed. So it is essentially there to capture the relevant flow features while recovering coarser mesh elsewhere. The model-driven AMR refines the mesh automatically with minimal user intervention until the final accuracy levels are met. Now, the key benefits are that fewer cells are created as a result, reduced computational expense, as well as the same accuracy as a static mesh. It's enhanced ease of use, and then finally reduces engineering time. And the next feature after meshing is its multi-physics capabilities. Now, STAR has a broad range of multi-phase and phase interaction models to predict and understand real-world problems. It's multi-regime, multi-scale, multi-phase. It has an efficient hybrid modeling to allow even the most complex problems to be solved efficiently while retaining, all the details. And one of the key things with Star CCM Plus over here is that all of the features, that may it be thermal flow, multi-phase, aeroacoustics, all of them are already unlocked in your base license. So you have the capabilities of doing, structural analysis, corrosion, electrochemistry, as well as the viscoelastic solver. Now, once you've set up the multi-physics capabilities, you also want to look into the speed and performance of the solver. So in terms of scalability, STAR is scalable to...
Before you move on to that, we had a question. Could you speak to the bidirectional connectivity with SolidWorks?
So there is no bidirectional connectivity that exists with SolidWorks. It did exist 2 years ago, but due to with the acquisition of Siemens and CD Adapco and Star CCM Plus, that connection no longer exists. But Star CCM Plus has a Parasolid kernel, and it is the same kernel that's used for SolidWorks. So there is no loss of data when importing SolidWorks part into Star CCM Plus.
Great, thank you. Sorry, please continue.
Perfect. So now, in terms of speed and performance, as I mentioned, we have the scalability of STAR, which is up to hundreds and thousands of cores. But now, looking at the mesher, that is also parallelized. So here's an example of a graph showing the scalability of the meshing process in the gas turbine combustor. It took 67 million cells to mesh in 12 minutes, which would have taken 8 hours in serial. And similarly, another compressor, which was 60 million cells, it took 18.5 minutes versus 9 hours in serial. Clearly, there is value in reducing the pre-processing time, especially when running large models. Now, all the images that I showed today and all the post-processing capabilities within STAR that was displayed today are all built in. It has a very powerful integrated post-processing tool. You can display simulation results in an easy, understandable context and seamlessly assemble and integrate and display results. It has volume rendering capabilities as well as capabilities such as screenplay that enable you to create such beautiful animations. But one of the key features with Star CCM Plus is that the ability to visualize the results live while the solution is running. This is great when trying to understand the flow behavior, but at the same time, it's also good in just making sure that all your boundary conditions are appropriately set up and not having to wait for hours to look at the results to understand those errors. Another cool feature is its virtual reality capability, where essentially you can use a VR headset to deep dive into the results. But one thing I did want to point out on is the entire workflow within Star CCM Plus, from CAD all the way to mesh, running an analysis, are all connected in an end-to-end pipeline. So any changes in the CAD will be updated down streamline. Now, this is available through the entire integrated process that is within every step of Star CCM Plus. Now, what if we took any of the parameters that the CAD's been built in and any of the solution parameters, such as, let's say, pressure drop, and want to study the best conditions in minimizing the pressure drop to give you the best CAD parameters. So within Star CCM Plus, the optimization tool is fully inbuilt. It leverages the Heath design optimization technology in doing so. So essentially, for today's overview, all I wanted to show is that here's the fundamental challenge, that if you look at how engineers are spending their time with simulation, even in organizations, you're most likely going to see something like this. Most of the time is spent building the models and running the first test. So much time, in fact, that little time is left for exploring the design space and assessing results to identify better families of design. Now, as we discussed, through the value, as we discussed, the value extraction is much higher from the time spent exploring and assessing. So there's a clear mismatch of the effort expended and value. What's required is a solution that better aligns resources with that value, so that engineers can focus on engineering rather than building computer models. So armed with this knowledge, Star CCM Plus design team, they set out to build a streamlined virtual prototyping solution to achieve this and to help discover better designs faster. Now, as I mentioned, this solution is comprised of multiple pillars that really define who we are. And so, we provide innovation products and technologies that are focused on helping customers quickly predict real-world performance and find better designs. We've devised, a unique flexible licensing model that makes design exploration possible, even for complex real-world problems. And finally, we provide a model for individualized customer support that ensures organizations can succeed in making the shift in simulation strategy through knowledge transfer and expertise. So this marks the end of my presentation covering the overview of Star CCM Plus. Now, the next part of the simulation, next part of the presentation, we're going to run a simulation, essentially a workflow demo simulating a Francis 99 hydroturbine. So the first thing about CFD simulation of Francis 99 hydroturbine, you're looking at understanding the hydraulic performance, the turbine characteristics, the cavitation behavior, and essentially we also want to look at the effect of a blade-shaped design, or maybe even the angle of attack of these blades through the compressor. So to do that, Star CCM Plus provides a fully automated meshing pipeline, a multi-physics platform, all done in one simulation. So we'll look at turbulence, conjugate heat transfer, cavitation, and a wide range of post-processing capabilities. But another key feature that we're going to look into is design change. And in this given simulation, we're going to look at the guide vane angle and modify that guide vane angle to see, let's say, the pressure drop performance or even the power output performance in this Francis 99 turbine. So similarly, as I'd shown before, we're going to go through the workflow demo, starting with the geometry import and transfer. So I have the parasolid parts associated with these files that are going to be imported. We're going to test out the import in two ways. One is directly through the CAD import within Star CCM Plus, but I'll also show you some of the features of bidirectional CAD associativity. So I'll be showing how that CAD can be imported within Star CCM Plus and then into NX and then directly connected to Star CCM Plus. Then we're going to look into setting up the physics, setting up the boundary conditions, generating the mesh, and then we'll solve the simulation. And once the solution is resolved, we're going to look at different post-processing capabilities. But one thing we'd also try to do is connect this tool to the design exploration capabilities within Star CCM Plus. So before I begin the demo, what I'd like to do is load up Star CCM user interface and just give you a quick introduction. So when most of you have completed the installation of Star CCM Plus, this is the window that will appear. Now, Star CCM Plus has a client-server interface. So what you're seeing right now is the client, and whenever a simulation is run, it is pushed onto a server. So there are two different interfaces, and the idea behind this is that you can easily build your models on a client. It could be your own laptop, but be able to essentially resolve it on a cluster through a server. And these two are two separate links, but enables you to use multiple resources at the same time. So first things first is, once once you've loaded the Star CCM Plus, to verify whether all your licenses have been set up correctly, you'll have to create a new simulation file. So once you hit the create new file, a window will appear. This is where you set up your what options you would like to use for in terms of processes. So here you can select the number of cores you want to use. Now, many of you within the Hands-on Simulate series have been given Power Session licenses. So I'd like to check your licensing file and see whether you have a Power Session license. What this provides you is with unlimited number of cores. So make sure to activate that if you have a Power Session license. Another license feature that I'd like to introduce you to right now is the Power on Demand. So this essentially gives you unlimited core usage for an hourly basis. So for users over here don't use Star CCM Plus constantly every day, or you use it, once every 2 to 3 months, they could just get a bank of hours and use the Power on Demand license to use those, use Star CCM Plus on an hourly basis. This also activates unlimited number of cores. So once you click OK, you're going to see a output window, and essentially the output window looks into the connection between the client and the server. So the first thing that will appear is the checking out of the licensing. So once you've clicked OK and you've seen the simulation tree populate with items, that means your licenses have been checked out and you are good to go. So for anyone who has not been able to reach out to this step, please don't hesitate to reach out to me. I'll leave out my email towards the end, and we'll make sure to ensure that you have your licenses checked out and Star CCM Plus fully installed. Now, note that this recording will be provided to you, so you don't necessarily have to load the tool for this session. So I'm just going to quickly run through the user interface over here and just give you an introduction to what we're seeing. So first things first, on the left-hand side, you will have the simulation tree, and this is essentially where we build our entire model. In this case, here are folders, and each folder is associated with different subdomains. So you have one folder for geometry. Continuum is basically setting up the physics. Regions for the boundary conditions. Setting up the stopping criteria. Looking at simulation history files. This is if you want solutions from external files. We'll talk about this more later. Monitors are basically points to extract data throughout the simulation. Plots to look at plots. Layout views is if you want specific custom views out here. Summaries, and then tools. We'll talk about some of these features in detail. Just note that every time you click on a given box or feature, you have a properties tab that associates the properties associated with the window. And then you have this large empty screen, which is the scene window. This is where you visualize data in terms of either geometry, vector properties, or scalar properties. I think a lot of this will make more sense as we build up the simulation file. I'll just give you a quick overview of what's on the top bar. So the first section, you have, create new file, opening a file, saving them. Out here is to copy, undo, or to move up the tree. Then you have views for recording macros. Now, Star CCM Plus has a Java API, and so you can record a given macro, which will output it in a JavaScript that can be used to automate your processes. The next step in the feature tree would be mesh generation option. So importing some mesh, launching the repair tool, as well as generating the surface and volumetric mesh. Then we have the run options. The green flag is the initialize solution. Step is to move a given time step or iteration, and then run is for running the simulation, and stop for stopping the simulation. Next, we have buttons for visualizing the scenes, which is essentially windows where you can either look at a geometry, mesh, scalar, and vector properties. Then you have plotting options for editing the XY plots that will be presented in the scene. You also have options for animations. Finally, you have options for selections and other tools. Now, there are additional add-ons that you have to Star CCM Plus, which I'll talk about later on, but those will essentially appear out in this feature. So now that you have a quick overview of the user interface, what I'd like to do is jump into the first section of this presentation, and that essentially is, looking at the geometry or geometry transfer. This would involve creating the geometry, simplifying the geometry for CFD simulation, but also parameterizing the geometry for design studies. So all of this can be done within the inbuilt CAD tool within Star CCM Plus, and the aim is to simplify the geometry for today. For this given geometry, we're going to aim to simplify the geometry to contain one segment using a mixing plane interface model for the full 3D geometry. So this is what we're going to achieve for simplifying the model and using mixing plane interface for this segment in the runner, so as to not to model the entire region correctly. So before I jump into the inbuilt CAD tool into Star CCM Plus, what I'd like to do is open the NX CAD modeler. So here we have imported a different body parts associated for the simulation. So you have the draft tube, you have the runner, and then you have the spiral casing. We also have a guide vane. And for this simulation, what we're going to achieve to do is to modify the guide vane angle to run our design studies. Now you can see that the guide vane is only in one section. What we also need to do is create a pattern geometry and subtract it from the runner segment. But earlier on in the presentation, I had talked about something known as associated modeling, or synchronous modeling. So one of the key features within NX is your ability to modify any dump CAD and create a feature. For example, let's say you want to move this given space and create parameter for and let's say you want to change to 30 millimeters, and okay, what we see is that feature is saved in a history. But one of the key features about this is now we have a parameter where we can edit and modify the geometry, for example. All right. So let's say we want to run a simulation within the CAD that can be done. So within the NX by CAD associative.
Hi, everyone. Yeah, Yafis is having a slight issue with his audio. He's fixing it in the meantime. Just bear with us for a minute. In that time frame, just a couple of key points for you. So as we mentioned, this is an introductory session. So that's why we presented the overview of Star CCM, and we're going through fundamentals. I'm sure some of you have more familiarity with Star CCM, so some of it may be redundant or it might just be a nice refresher. We will get into more in-depth subject matter expertise later this session as well as in other sessions, so do keep that in mind. In addition, Star CCM should be made available to you in terms of licensing, whether you have it or as part of a trial in relation to this series. So if you have issues in relation to installing it or getting your license to work, we strongly recommend you please reach out to us. We'd be happy to help you get that sorted, as what's going to help moving forward is as we make these recordings available, as well as the files that Yafis is going over available, it'd be great if you tested it yourself and then reached back out to us if you had any specific questions. So with that, I believe Yafis is back. Yafis, can you confirm and keep us rolling?
Perfect. Yeah, apologies for that. Some of the
all yours.
Negative parts of working at home. Perfect. All right. So what I just recently did was creating an operation of moving the face. Now, what we could do within this bidirectional CAD associativity is run an entire simulation within the NX CAD. So any changes in the CAD would update with the solution. So here you can set up the mesh pipeline, set up the boundary conditions within the NX CAD interface. But let's say, for example, you'd like to use the same CAD parameters and transfer it to Star CCM Plus. Over here, you have this option called the design data. Here, it posts out the parameter that we just created, that is the motion of that face. That's the feature that's been created. We want to export that to Star CCM Plus, click OK, and all you need to do is hit transfer geometry. What's going to happen is Star CCM Plus is going to be launched, and this given feature of move face or this parameter will be exposed within the Star CCM user interface. So any changes that would be made to our geometry in Star will be updated within this feature. So let me show you a quick example. I'm just going to wait for the solution to launch. Once that's created, let's create a scene, and the scene is where you want to visualize data. Over here, we're going to visualize the geometry. So here's the geometry of that feature. But what you can see over here is CAD client modes. This is the part that's associated there. And then in terms of CAD parameters, we have that feature of, let's say, 300 millimeters. What we can do is change it to maybe 700, enter, right click, and update the model. So you're going to see the model update out here. But at the same time, you can see that the model has been updated within the NX CAD feature as well. Now, the key idea for why we're doing this is to parameterize the model for design exploration. So we can then use these CAD parameters directly into the optimizer without much of user input. So just a reminder, the bidirectional CAD associativity is there for CATIA, Creo, Inventor, and NX. However, it's important to note that there's a fully fledged 3D modeler in Star CCM Plus. So what I'm going to do is now basically show the same design feature that we've created in Star CCM Plus, but show you how that CAD modeler was used for essentially creating that slice that I earlier talked about. So as you can see over here, if you expand the geometry feature, you have 3D CAD model. If you expand that and click edit, the 3D CAD modeler will appear, and this is where you can essentially use a full-on CAD tool within Star CCM Plus. So one of the first features that were created is you've imported the different parts that we talked about. There's an extrusion of the inlet area just to get a fully developed flow. But then you also have operations for the creating the slice using the turbo slicer. And then we also took the guide vane and created a pattern geometry. Now, one of the key things that we did was when we created rotation in the guide vane at a given angle, and we exposed that design parameter. So all you need to do for that is when you right click, you edit the given part and you're defining the rotation. There's a feature out here that says, where this CAD parameters are here. Once you click over here, it says expose design parameter. Once you click on that button, what it does is that it exposes that design parameter to the user to update out here. And that same design parameters will be available to the optimizer essentially. So in this model, what we're going to do, as I mentioned earlier, we're going to optimize the design vane angle to look at, let's say, the total power and the effect of the total power on the design vane angle. Now, this is the CAD modeler, and these are the operations that were conducted here. But within the geometry, you can see that there is the operations window, and in the operations itself, you can do CAD changes as well. The difference between CAD changes that are made in the 3D CAD model and the operations is that these operations are associative to these models. So if ever I want to say test out a new design or a new draft cube, all I can do is right click and replace part. Once I do replace that given part, all the changes that I've made to this given part, for example, they will be associative. So let's say, for example, an operation you can do is in terms of filling holes, the surface render, or extract a given volume. But you can also do unite, extract, imprint, and bounded shape. But the same operations they move to the meshing process as well, and I'll explain to the logic to why mesh is part of these operations as well. So one operation that I'd like to point out is the imprint operation. Now, the imprint operation makes sure that any interface that's found between the different parts creates a conformal mesh. So one thing I'd recommend is whenever you import a given geometry, there might be interfaces between these two geometries. For example, in this case, between the draft tube and runner segment, and the runner segment and the spiral, you have these interfaces. What the CAD imprint does is that make sure that those faces are conformal and create a conformal mesh in that case. So we're just going to click OK. And here's the operation. It has a warning sign next to it that means it hasn't been executed. Hit execute. And once you've executed this operation, you can see that contacts have been created. What it means is that there has been an interface contact between the draft tube and the runner segment and the outlet and the inlet. And as you can see over here, conformal mesh has been generated between those two features. So every time you imprint, you create these contacts, and these contacts make sure that they're conformal out here. Now, if you don't have these contacts, you would have a non-conformal mesh. And what would happen is that you would have data transfer through a medium or through interpolation, essentially. But what we want to do over here is create a conformal mesh. Now that we've completed the geometry portion of the section, the next thing would be setting up the physics, that is understanding the model and setting up the boundary conditions associated with it. So I'd like to introduce you to two concepts over here. The first thing is continuum. So continuum is where you define the physics model. Now, what are these physics models? They are the type of simulation solvers you want to use. They could be 3D or 2D. They could be steady, transient, the turbulence models you want to use, the material properties. But within the continuum, you also define the initial conditions or any reference values, like reference pressure, for example. Now, this is not associated to any geometry, but if you want to associate a physics to a geometry, you create something known as a region. And so the region is where you set up the boundary conditions. You have interfaces between the different boundaries where you can, in our case, we will be defining a mixing plane interface, but it could be also a baffle, for example. So to clarify exactly what's going on here, let me jump right into the tool. Let's go back to our model out here. So once we have created a 3D CAD model, what's important to do is it creates these body groups. And these body groups are any given part out here. And what we can do is, for using these 3D CAD model into the simulation, we have to convert it into a part. So the advantage of this is, if imagine you have a 3D CAD model with thousands of parts, but you only want to use a few parts within the simulation, just right click and create a new geometry part. So that's what I've done for the draft tube, the runner segment, and the spiral casing. Now that we've created the part, we want to assign a region to it. What that means is that we want to assign some sort of boundary condition to these parts. So we assign parts to region, and the assign parts to region window appears. Now, you can create one region for all the parts, but we want to create a region for each part. And the reason we want to do that is because for the runner segment, we want to create a rotating part. So that region is going to be separate and that region will be rotating, whereas the draft tube and the spiral casing will be stationary. Now create a boundary for each part, but we want to create a boundary for each part surface. So each part surface is associated with the boundary condition. And then finally, this is create one feature curve for all part curves. Now, this is for when you're running 2D simulation. That's when you create a feature curve for each part curve. We'll talk about more that for those who want to do 2D simulations, but essentially the first two features are essentially for 3D parts. And then finally, we talked about contacts. So we want to create a boundary mode interface from the contact. So every contact that was created, we want to create a boundary mode interface. And that's true for this case because that's what we want to do for creating a mixing plane interface for the two boundaries associated with the draft tube and the runner segment and runner segment and spiral. Next thing is create a contact mode interface from contacts. We'll talk more about that in with regards to fluid structure interactions. But if for any given flow and thermal simulation, you just create a boundary mode interface from contacts. You click apply and close. Now, as you create these regions, you're going to see different things populate within the simulation tree. What we see over here is the interfaces have been created from the boundary mode from those two contacts, but also we've the three regions associated, and each of the face of each part is associated with a boundary condition essentially. So let's try to start by setting up some of these boundary conditions. So for, let's say, the draft tube out here, we want to set up a pressure outlet here. So as you click on the button, you see that its properties appear out here. So in terms of type, by default, everything is set to wall, and any other interface is set directly as an interface. So this is what it means by an interface. And in this case, it's set up to internal interface, but we'll change it later on to a mixing plane. So let's say the outlet wall, you want that to be a pressure outlet. And the other boundary condition we want to apply is for the spiral casing, we have the inlet where we want to put in a mass flow inlet. The other thing that we talked about is that for these given interfaces, it's an in-place interface. That means flow can pass through, or it's an internal interface, flow can pass through, but we want a mixing plane interface for both these features. So let me put this as a mixing plane interface. As you can see, the interfaces over here have been updated as well. Now, the next feature, what we want to do is, now that we have set up the boundary conditions and what the boundary conditions are to be applied, we want to set up the physics associated. That means what solvers do we want to solve in this given geometry? What are the, the solvers that we want to activate? Is it a steady state or transient? And this is where you do it in the continuum. So you right click, create a new and create a physics continuum. So you'll also see the option for mesh continuum, but this option is going to be, it's not going to exist there within from 2021. It's an outdated feature that's no longer being used, but has been used by some of our other clients. So whenever you create a continuum, just use a physics continuum out here. Now, in terms of the models, you right click and you hit select models from the drop down menu, and you have the various features that appear out here. So first things first, this is pretty easy to set up the physics. In terms of space, what type of simulation do you want to run? A 3-dimensional, 2-dimensional, a shell simulation, or an axisymmetric. In this case, we want to run a 3-dimensional simulation. In terms of the material, it's going to be a liquid one, but you can do multi-phase, multi-component liquid, or multi-component gas. Select liquid. In terms of flow, there are 3 types of flow solvers: the coupled flow solver, segregated flow solver, and viscous flow solvers. All I need to tell you is that coupled flow is mostly for supersonic and hypersonic flows, where you want all the pressure, velocity, and momentum equations to be coupled and solved simultaneously, whereas segregated flow is for mostly incompressible flow. So that's what we're going to do in this case. In terms of equation of state, we're going to select constant density. And then in terms of time, steady state. But it's as easy as unchecking steady and selecting implicit unsteady for running an unsteady simulation. In terms of viscous regime, we're going to select turbulent model. And as you can see over here, okay, so we're going to select the K epsilon model. But one thing you're going to see is that some of the models we haven't selected have already been selected out here. And that's because of a auto select recommended models feature that appears out here. So let me just deselect this and try to select the models out here just to give you an idea of what this unlocks. So in terms of, you know, turbulent model, you have the advanced simulation available. But let's say you want to do the K epsilon model, so you have all these various K epsilon models that will appear. So the star is what's recommended by star CCM Plus, that we use the reliable K epsilon 2-layer model, but you have all the other K epsilon models available to you. And then you have the 2-layer all Y plus wall treatment. This ensures that irrespective of what the Y plus is, if it's below 5, then it's going to use the explicitly model the Y plus versus above 30, then you use the log law function. And now once you've selected all your models, so all these are the optional models. Like I said, there's a wide range of physics capabilities available within Star CCM Plus. Now, if you want to activate adaptive mesh refinement, all you need to do is click on that. There's aeroacoustics. You have DMP model for dispersed multiphase. You have electrochemistry, electromagnetism, gravity, if you want to activate the gravity out here. Then segregated fluid enthalpy for activating the energy equation. But all it takes is a few clicks of a button and you're complete. Another key feature that I'd like to mention is the co-simulation model. So you can connect Star CCM Plus directly to other tools. So some of the tools that we can connect to is a 1D solver called AMOSIM. You can connect to Nastran, SimCenter Nastran to do fluid structure interactions, but you do have a structural solver within Star CCM Plus. So that's the selection model. So once you've selected the models, you're going to see this turn into from blue to gray. That means all the models are complete. If you expand the sector, you're going to see all these models available out here. This is where you apply the boundary, the material properties, and water is set as the default property. You also have the reference values because all the measurement in terms of pressure engaged. So you have the reference value set to atmospheric. You can definitely change that if required, and also the initial conditions associated with that continuum. Now, in terms of the physics, you can see now that each of these regions is associated with this physics. So all the draft tube, the runner segment, and the spiral casing will be using these specific models. Now, let's say, for example, you had another, solid part or the casing, actual casing for the draft tube, then you would create a new physics associated with a solid. And, let's say you want to select the model and you want to run 3D. Now you're solid and you say steady. You could activate the finite volume stress energy solver to activate the solid stress model to activate the finite element solver for solving the solid. But you can then say if this was the actual draft tube, you change the physics from physics 1 to physics 2, then it'll be modeled as a solid. So that's the relationship between continuum and region. So continuum is where you define the solvers that you want to define, and regions is where the boundary conditions are defined. Now, it's pretty intelligent in the sense that if you select a region associated with this fluid, the boundary conditions available out here are going to be those associated with fluid as well. We have a few other boundary conditions yet to apply. One thing we need to do is set up the periodic interface in the runner segment. So if you expand the runner and you look at the boundaries out here, you have the two periodic faces. Select both of them using control, right click, and create an interface. So what happens is that when you click two boundaries, it's going to create an interface out here. And instead of an in-place internal interface, we want this to be a periodic, this internal interface, the topology should be periodic. So that's going to be an in-plane interface. And in terms of topology, we want it to be periodic in this section. And that's all you need to do. Now, once this is set up, we also need to set up the runner segment to be a rotating region. So if you expand the boundaries, you're going to see physics values out here. This is where the motion specification is going to be. Right now, it's stationary with the lab reference frame to what's the default setting. That is the universal coordinate system that's out here. But if you want to create a rotating region, you have to go to the tools. Now, if you go to the tools section, and the tools has various options available to you. You can create field functions here. You have the material database if you want to import, screenplays to look at, create those images. But in this case, we want to create a motion. And in this, you have different types of motion available. You have DFBI, that's dynamic fluid body interaction. If you want to do physical motion, solid displacement, trajectory. In our case, we want to do a rotation. Another motion that's available is morphing for mesh morphing. So it's as simple as creating a motion capability, defining the axis. So this is going to be in the Z direction. And in terms of rotation rate, we're going to set this up to minus 35 radians per second. That's going to be in the opposite. So taking the right-hand thumb rule. Once you've created this motion, go back out here in the motion specification. We don't want to create a rigid body motion. We want to create a motion that's a rotating frame of reference. So we change it to the reference frame for rotation. And that's all that's required in terms of the setup. We do need to set up the inlet condition. So set up the mass flow rate for the inlet condition, which we haven't defined yet. So you go to the boundaries, here's the inlet, expand that. So in terms of the physics condition, we said the mass flow option is going to mass flow rate. And in terms of the physics value, we want to set that up as 200 kilograms per second. All right. So one thing I do want to show that's pretty cool about Star CCM Plus is the ability of being neutral to units. So if you ever want to change this to 200 inch per second, that's all you need to do, or 200 millimeters per second, and that feature appears. Oh, sorry, because there's a syntax error because this is in kgs and not in millimeters. I apologize for that. So let's say it's going to be grams per second or any pounds per second. You can set up the units directly. So this is going to be 200 kg per second. All right. So essentially, we've set up all the boundary conditions associated. So I'm just going to go through a quick overview of what I just did. We had the geometry being imported, all the CAD parameters being set up within the 3D CAD model. Then the parts we wanted associated to be run in the simulation, we created parts out of them. Then we created an operation called the imprint operation to make sure everything was conformal. We then assigned parts to region so that we can apply the boundary conditions. We set up what the boundary conditions were. We created a physics continuum to set up what type of physics we want to solve. And we set up the exact values for the boundary conditions as well. For example, the inlet to be 200 kilograms per second, and the rotation for the runner segment, and setting up the periodic interface for the runners. So that essentially covers the first section of the session, where we talked about two things in particular that were important. That is the continuum to where the physics models are set up, and next thing, the regions for where the boundary conditions are set up in the interface. Now, the next portion we're going to talk about is the meshing. Now, Star CCM Plus is an automatic mesh pipelines within the operation. We'll talk a bit about mesh controls, and then we'll talk about the mesh diagnostics, how to look at whether your mesh is a good mesh or not. So out here, as I mentioned earlier, the meshing process is in the operations. And one of the key reasons why this is there is that any operation is conducted from top to bottom. So it's a series of operations where you can change which operation occurs first or the second. But let's say, one of the operations could be rotating the vane angle. So you could create it as an operation, put a segment, then mesh it. What you can do is then any change to the geometry is run through that series of operations. So the first operation that will be conducted will be imprint operation to create those interfaces. Then the next operation that we want to do is create the mesh. Now, there are multiple meshes available out here. You have badge for 2D meshing. So if you want to create some sort of 2D mesh or an extrusion from a 2D mesh, there's a volume extruder. You have the directed mesh as well, and the volume mesh pattern if you want to create a pattern for a given volume mesh. But in this case, we're going to create the automated mesher. So this is the automated mesher within Star CCM Plus. Here we select the parts we want to, mesh in this given tool. And then in terms of the surface meshes, we want to create a surface remesher. What that means is the mesh is going to be extruded from the surface itself instead of just a volume mesh being created. So it's usually activated 99% of the time. You also have an automatic surface repair option. If ever you'd expect a lot of skewed cells or geometry that's not very clean. In terms of core volume meshers, you have three types of core volume mesher. You have the polyhedral mesher, that's for nice swirling flows, but you also have the tetrahedral, the traditional tetrahedral mesher, and then you have the trim cell mesher for usually used for external aero unidirectional flows. So in this case, we're going to select the polyhedral mesher. Then you have other optional volume meshers. So you have two types of volume meshers, the thin mesher and generalized cylindrical mesher. So this creates a generalized cylindrical mesher creates a clean mesh for cylindrical domains, but also thin mesher is creating a structured mesh in regions where there are small or thin gaps. So this is key whenever you have geometry where you have a small gap, and if you created, let's say, a prism layer mesh on each of them, it would just create an extremely skewed mesh. So that's another volume mesher available. Then in terms of the boundary layer mesher, you have two types of boundary layer mesher. The prism layer mesher, this is the traditional boundary layer, but also the advancing layer mesher, which is for external aerodynamic applications. In this case, we're just going to use the traditional prism layer mesher. Click OK. And then you have the mesh operation appear out here with a sign that's saying that it hasn't been executed. So the first things first, in the first window appears is the mesher and the three different types of mesher and the properties associated with it. In this case, we'll not go deep into what these properties are, but essentially the default options are generally used in most cases. Now, in terms of the default controls, you're going to see that you have the base size, and then you have other sizes such as the target surface size, the minimum surface size, and all of them are relative to the base. This is useful when you're running mesh independent studies, so you just need to change the base size and all the surface size. Even, let's say, the prism layer total thickness is relative to base, but if you know the thickness, you can also set up an absolute value as well. That option is available to you. So let's quickly set up a few parameters out here. So for the base size, instead of 1 meter, we're going to hit 5 centimeters. For the minimum surface size, let's say 20% to the base size. And then for the total prism layer total thickness, that's going to be too large. Let's set it up to just 5%. Now, this is just the default controls, but let's say you want to add custom controls. Now, custom controls could be on a curve, on a surface. It can be on a given part, but also volumetric control. So volumetric control is, let's say you can just import a given body out here and create, let's say, within this region, you want to create a much finer mesh, or at the outlet over here, then you just create a big box and then create a volumetric control associated with it where you want it to be refined. And that body does not necessarily have to be part of the simulation. So in this case, what we want to do is create a surface control. And for my surface control, what I'm going to select is all the inlet and outlet regions, as well as the periodic regions. And I don't want any prism layer mesh associated with it. So you just expand that, all the inlet and outlet regions, the periodic faces, as well as, for the spiral casing, the inlet and outlet region. Just going to click OK. And now we have all these surfaces selected. And in the controls, you're going to have prism layers. And we just want to disable them on those interfaces because we don't want any conformal, any sort of prism layer in the periodic regions or in the interfaces of those regions. One thing that I do want to mention is that by automatically, Star CCM Plus will not create a prism layer mesh on any inlet or outlet boundary condition or a periodic boundary condition. So we necessarily didn't need to have to disable the mesh out here, out there, since Star automatically disables them because they will never be required. So there's some sort of intelligence associated with this tool. Now, the next step is generating the mesh. Now, as I mentioned, the meshing process is parallelized. So when you click on the automated mesher, you have the option of mesh execution. We're going to hit parallel, and we could, initially extract the surface mesh to look at it, but we're just going to automatically just go right ahead and generate the volume mesh. Now, this is going to take a minute or two, but essentially, just to give you a few tips out here. So you're just looking at what's going on between the client and the server. So the mesher is running in parallel. So this is the output window that's setting up for the information and data at which stages the meshing is available. What I'm going to show you next is mesh diagnostics. So there are multiple ways of looking at mesh quality. You can essentially look at individual mesh qualities within the scene, but also you have a feature over here called mesh diagnostics, which will enable you to look at face validity or face normal. While this is running, I'd like to just open the help section or of Star CCM Plus just to show you some of the features out here. So this is, when you hit the help section, you get to the guideline out here. Within Star CCM help section, you have, 3 features. So this covers the CAD clients, if ever you want to connect the CAD clients. But also we have, the tutorials available to you. So if you go to Star CCM Plus, and you go to tutorials, here are all the tutorials associated with Star CCM Plus. You have the basic introduction, which most of what I've covered would give you an understanding. But if you want to do specific motion tutorials or reacting flows, all these features are available out to you. Now, in terms of where the files are given, I do want to show you the support center. So most of you who've already got Star CCM Plus installed, when you open your support center, you should see My Products. If it does not appear, please hit Manage Products and select, a missing product out there. So once you open the Product Center, click on Downloads. This is for those who've installed it. You can, select the version, click out here, and then once you've done that, you're going to see the Linux version and the Windows version. I have the Windows version, and then you have the tutorial files out here. It's a large file, but it contains all the files associated with the tutorials that I just showed earlier on. But one thing that I do want to show about Star CCM Plus is that the search feature is quite complex. So it's more than just tutorials. So let's say I do fluid structure interaction. And what you're going to see is this large documentation, which is going to go through not only just say a spotlight, which gives you a full idea or introduction to what fluid structure interactions in Star CCM Plus is, but also it has questions and seminars on fluid structure interactions. You can actually see examples of vortex-induced vibrations. So if you go out here, you have the options of looking up, the knowledge base, but also searching the documentation. And so it's a quite expensive issue. But let's say, for example, you cannot find what you want in the support center. Please don't hesitate to email me. I will provide you my emails in terms of questions and concerns. We can set up one-to-one sessions just to make sure that everyone gets to use the tool smoothly and efficiently. So the meshing process has been complete. Now, once the meshing is complete, you want to visualize the mesh. So you create a scene, a mesh scene. So this can be done through the top toolbar, but you're going to see that there's also a window, a folder out here called Scenes, where you can right-click, create a new scene, and visualize the mesh. So essentially here you've seen the polyhedral mesh that's been generated. What's cool about Star features, sometimes if you say, for example, you just want to scroll in and it'll deep dive inside the mesh so that you can see some of the features within the domain. So this is a pretty cool feature. So you want to look at internal mesh surfaces, and instead of doing cut planes, you can just scroll right into the domain. Right. So that covers, just if we can create cut planes, and we'll talk more about that in the post-processing section. But essentially, we have completed the meshing process. Yes, I forgot to show the mesh diagnostics. So you go to hit mesh diagnostics. So you have 2 types of representations, either in the volume mesh or just the geometry. But you can also create a full report or a compact report. Click OK. Once you create a compact report, one of the main features you want to see is that the mesh is topologically valid and has no negative volume cells. So this is key. You don't want any negative volumes, or the solution is going to crash. and you want the face validity not to be less than 0.5. So that means, and then in terms of volume change, obviously you want something with less volume change so as to not create any sort of skewed cells. So now that we've completed the mesh generation, I'd like to just jump right into the solving. So in terms of solving, it's pretty simple. You're looking at two things: the solver settings and stopping criteria. We've already selected the solvers in the physics. So if you close out here and if you expand the solvers, you're going to see all the solvers activated. So the steady state solver, the segregated flow, the turbulent solver. You have settings for each of the solvers, such as under relaxation factor, each of those features. One thing that I do want to mention is once you activate the unsteady solver, you're going to see the unsteady solver over here, and that's where you can change the time step for that given solver. And then in terms of stopping criteria, you have the features out here. Because earlier on I'd activated the unsteady solver, it just showed up as the inner iteration. This is for the inner iteration maximum time step. As you can see, they're deactivated as they will not be used since we have a steady state solver. But in terms of maximum steps, let's, for example, set this to 200, and that's it. So pretty much the solver settings is pretty straightforward, not too complex. Based on whatever settings or physics you've activated, the solvers will appear out here. And now the next portion is just going to cover the post-processing capabilities. So in terms of post-processing, there are three main things that we want to do. First thing is define the region or places where we want to visualize the results. So that'll be through derived parts, or create new field functions to look at, let's say, for example, you want to create your own variable and you want to visualize that in the domain. You can create your own user field function, but then you also can create reports and monitors, and this is to visualize data on a given part, surface, point, line, and monitor throughout the simulation. So you can visualize them as the solution is developing. Something we're going to create is, let's say, match flow rate at the outlet, or just to look at convergence, for example, or even the pressure drop between the inlet and the outlet. Then next thing is showing. What that means is that you want to visualize the results in 3D. So this could be done using scenes, and this is what I'm going to show today. Is a scene, and you can visualize the results in real time as the solution is developing. You also have 3D volume rendering. You have XY monitor diagrams. We're going to cover through that as well. And the last step is going to be sharing the data. So you can easily share the data through CSV tables, export them, import tables, create images, animations. You can also create 3D visualization files, which can be used where StarCCM Plus Viewer will be used to visualize that data. You've already got access to a StarCCM Plus Viewer. For those who've installed Star, you're going to see a second icon appear. If those who have installed the VR headset, they have that as well. And that viewer is essentially something that you can, share 3D scenes or visualization to your customers if they want to look at that data in a 3D environment, essentially. So let me jump into the simulation and just cover some of the things. So derived parts are regions you want to visualize data. So let's say you want to create a derived part for a plane section. So you have this feature available to you. So let's say you want to create in the Y section, and we want to create one in that direction. And let's say you want to create one in different planes in different sections. You can do that pretty easily. So those are the derived parts that have been created. And one thing that we want to see in this given derived part, let's say you want to visualize just mesh on that surface and visualize the domain. So we go back to the mesh scene. So you have two sections. This is the mesh part that we want to see. So out here in the parts, let's just hide that, and we just want to show the derived parts. We can look at in this given plane section. How does the mesh appear? So you can see this is in 3D. All right. So you can also look at the boundary layer mesh that's been generated. You can create different planes to visualize the sort of data. But other than planes, you can also create derived parts in terms of points, if you have probes or lines, if you have a series of probes, then streamlines. There are thresholds where you can only visualize, let's say, velocities between 2 meters per second, 3 meters per second, or any other field function. Resample volume, also warp, and this is mostly for looking at displacement of body in fluid structure interactions. We'll cover that if it comes to that. Now we've talked about scenes in terms of geometry and mesh, but you can also create scalar scenes. And in this case, we can just take that plane section, drop it out here, create a scalar as well as the outline feature. And in terms of field function, just right click and you have all the field functions available. So we can hit velocity and magnitude. But if ever you want to just go back, you can go to the scenes. Within the scalar section, if you go out here, expand the scalar displayer, you can change the field function out here as well. So it's either within the UI or within this window, all of the features are appeared. So when we run the simulation, you're going to see the velocity magnitude actually, being displayed every iteration out here. So other than looking at visual data, the other things that we really would want to see, let's say, is mass flow rate at the outlet. Just look at convergence. So you can create a new report and create multiple types of reports. So you have user-defined reports in terms of expressions, maximum, minimum, but you have system reports in terms of solver CPU time. You have overset for overset meshes. We can touch that later on, but you also have metric reports to look at surface average, volume average. But in this case, you can also look at flow energy, look at mass flow average, velocity in this case, or to look at the, just to understand the convergence. So I'm just going to search for velocity out here. The other things that would be relevant is to look at pressure drop, for example. So if you right click, create a new report and create a pressure drop report. So I'm just going to activate. So the high pressure phase is going to be the inlet, and the low pressure phase is going to be the outlet. And so once you've created a report, let's say you want to visualize the report every time step or every iteration, you would right click and you would create a monitor from the report. And monitors are basically data that's collected through every single given iteration. So you have monitors for continuity equation, for looking at physical time, pressure drop, the XYZ momentum. So the blue ones are defined by the solver, and the gray ones are the ones defined by the user, which can be deleted, but the blue ones cannot be. And so let's say you're now collecting this data every iteration, that's the trigger, and you're looking at a given value, but you also want to plot it. So you right click on the monitor and create a plot from the monitor, which will automatically create pressure drop versus iteration. But another cool feature is if you click at the mass flow average, create monitor and plot. So it's going to do it automatically, create the monitor and the plot together. So reports can be visualized in the simulation at any given time step through creating monitors. So this is data that's been collected. And then all the monitors, you can plot them to visualize information, essentially. So you have the one for residuals automatically created, which visualizes the residuals of the XYZ momentum and DR and PDK values. And that essentially covers some of the features of post-processing. These are just the basic. We can talk about animations, screenplays, but we're going to leave that for you to explore through the tutorials, or we'll go through some of those features as well throughout this hands-on simulation series. So now once we've essentially set up all the scenes, it's ready to run the simulation. So I've already created a file with some of the post-processing capabilities that I'd like to essentially show. So I've created scenes for looking at the velocity vector, or looking at pressure on different planes. Over here, I've also created derived parts at different points in the domain, plane section. So as I showed out here, and so all we need to do now is just run the simulation and essentially visualize the results in real time. So this essentially is, as the solution is developing, as you can see out here, this is the iterations, the solution is developing, you can visualize the results. You can look at, let's say, I've also created a report for looking at total power, the mass flow averaged at the output as I showed earlier on. So once this converges, one key feature over here is, we talked about stopping criteria, and we looked at stopping criteria in terms of just steps and features, but you can also create stopping criteria with regards to reports or, sorry, the simulation is still running, but you can create a new monitor criteria which looks at, if the delta in the mass flow rate is less than 0.01%, stop the simulation, which is a cool feature if, where you don't need to run the simulation for 2000 iterations essentially for it to develop. So this is the simulation being run. Now, what I also, so while the simulation is running, I do want to touch upon the last and final feature of this presentation, and that is to look into design exploration. So essentially, in design exploration, there are two things that we want to talk about: is parameters and the design manager. So all the parameters that we've created will be exposed to the design manager, and the design manager is where you can run sweep studies, optimization studies, DOE studies. Now, for the design manager, you can run all the other given studies except for optimization. You need a intelligent design exploration license for it. That's an additional license. But if you want to run sweep studies or any other study, you can do it using the design manager, and that's what I'm going to show you right now. But also, I want to show a pretty cool feature. We're just going to let the simulation run up to 200 iterations. And I'd like to expand, let's say, on the geometry out here and look at the 3D CAD model we talked about, we had created earlier. And we had the guide weight angle set up to that given degrees. So let's just change it to 12 degrees. And once you change it to 12 degrees, you're going to see the operations have the caution sign. So you want to execute all the operations. So what it's going to do is going to re-imprint the parts. It's going to remesh the parts with that angle change. But one of the other coolest features is that you're not going to restart the simulation from scratch. It's going to take the previous simulation, map it onto this given solution, and run the solution from that given iteration, essentially saving you a load amount of time when running design exploration studies. And this is one of the key features that enables you to run hundreds of design within Star CCM Plus. So while that's at it, we're just going to wait for the solution to update till I load up the design manager. You just have about 5 minutes to the top of the hour, but running the design manager is going to be quite simple and easy. So I'm just going to go jump into the other simulation that we had created to look at the design manager. So once you've created a simulation, you run your first file, and now you want to, let's say, run a design study. So in the simulation file, right click and click create design manager project. And what's going to happen is it's going to load up the design manager, where you're going to select the the requirements for what would be needed for an optimization study. Now, for any optimization study, you have to have the input parameters, you have to have a response, and you also want to have scenes to visualize the data. You also want to then basically set up some of the constraints as well as the objectives. So out here, we've created the design manager project. Out here is the simulation file we've selected. So we want to create a new study. In this new study, let's say we want to run a sweep analysis, but we can also run, say, an optimization case. So inside the input parameters, once we click here, you're going to see the guide weight angle already exposed. So any parameter we have created out here will be exposed out here. They're not only subjected to just the CAD, but you can do any given design parameter. So to do a design parameter, if you go to the tools, you're going to see this is alphabetical, so it's parameters. You can create parameters that could be scalar, vector, or even a file. And all these parameters will be exposed to the design optimization study. Now, in terms of responses, we're going to have the mass flow average and the pressure drop. So if you want to minimize the pressure drop, but also make sure the mass flow average is constant. So these are the responses we want to look into. Now, if we expand the responses, we can see, is this an objective? Is this a constraint? Let's say in the pressure drop, this is the objective. We want to minimize the pressure drop as create a minimum. Now, what scenes for each simulation, it's going to save up the scene. So all the scenes we've created in terms of the pressure scene are available, mesh scene and geometry scene. So I want to save all three of them for each of the files. You don't necessarily have to save the sim file as it can take a lot of space. And finally, the plots. What are the different plots that you want to do in terms of pressure, average pressure drop, and residuals maybe? And that's it. And you're ready to run your design study. You do have to maybe set up some of the input parameters. For example, it's already set up some default values, but it wants to look at the guide vane angle from 7 degrees to 12 degrees. And all you need to do, since the caution button's away from the design manager, all you need to do is right click and run the study. So this essentially ends or marks the end of the simulation, first session of the simulation series. Just go through a quick overview of what we did for this given simulation. We looked at creating geometry in the inbuilt CAD tool. We looked at creating the parts. Then what we did is we created regions to assign the boundary conditions, physics to define what are the solvers we wanted to use. And then finally, we created post-processing parts or derived parts to look at different planes, reports to look at data, and monitors to look at the data live as the solution is developing, and finally different scenes to visualize the data. But we also leveraged the CAD connectivity where we changed the CAD angle, updated the simulation, and for this given simulation, we're just going to run, and it's going to, it's at the stopping criteria. I'm just going to expand the stopping criteria to, let's say, 400 iterations. And so it's going to leverage the same workflow and reuse the same simulation and not waste time in rerunning simulation from scratch. So the geometry has been updated, but we also talked about the design manager to leverage these same parameters for design optimization